This is Dr. Shankaraiah from Department of Physics. In this presentation, I am going to discuss about characterization techniques from Module 5, Nanotechnology. So, two characterization techniques I am going to discuss about: X-ray diffraction and transmission electron microscopy. Most of the metals and alloys are crystalline in nature. So, most of them, metals and alloys are crystals. Okay. So, most of the metals and alloys that we see in nature are crystals. Okay, hence one of the most useful characterization techniques is X-ray diffraction, which we are denoting it as XRD. So XRD is X-ray diffraction. So XRD is used to look at the whether the given material is a crystalline, or if it is a crystalline material, what is its crystal structure. Okay, so that is why X-ray diffraction is very important techniques or characterization technique to study these metals and alloys, which are mostly crystals. XRD is done Bragg's law. So Bragg's equation, as we know, Bragg's proposed that if there is any diffraction, okay, Bragg's equation for diffractions. So Bragg studied the diffraction in crystals. Okay, so if there is any diffraction in crystals, then this equation must be satisfied, that is 2d sin theta is equal to n lambda. So where d in this equation, d is interplanar spacing. Interplanar spacing, and theta is angle of diffraction. Theta is angle of diffraction, and n is order of diffraction. Order of diffraction, and lambda is wavelength of the incident light. So if we are irradiating a material, a crystal, with light which is having wavelength lambda, then if there is any diffraction, then this equation 2d sin theta must be equal to n into lambda, where n is order of diffraction and lambda is wavelength of this incident light. So how do we know what order? So if you look at this intensity pattern, intensity distribution, intensity versus angle, so angle, then at theta is equal 0, we have highest peak in intensity, and as we go away from the center, we find the intensity distribution will decrease as it will decay to 0 for larger distances. So at the center theta is maximum. So yeah, so from the center, if you take the first peak right side and first peak on left side, so both of these corresponding to n is equal to 1 are first order diffraction. Then from the center, the second peak on left side and the second peak on the right side and left side. So these two corresponding to the second peaks on both right and left side from the center, both of them corresponding to n is equal to. So from the center, third peak from right and third peak from left, these two corresponding to n is equal to 3, which is third order diffraction. So this is how we can find the order of diffraction. So the intensity of diffracted X-rays is measured as a function of the diffracted angle and the specimen orientation. So that is how we can find out the order of the diffraction using plotting intensity versus angle. Okay. So if there is any diffraction, this Bragg's equation will be satisfied, that is 2 sin theta is equal to n lambda, and then we will also find out whether the diffraction is first order or second order. So this diffracted pattern is used to identify the specimen's crystalline phases and to measure its structural properties. So by looking at this diffraction pattern, we can identify whether the given material has which crystalline structure. So there are 7 different crystals which we know, right? So by looking at the diffraction pattern, we can find out the given material is which crystal. Tetragonal, orthorhombic, cubic. Okay, so that we can find out using this X-ray diffraction pattern, and we can also look at its structural properties. So XRD is used to find out if there is any diffraction on this crystal. We can find out its crystalline structure and its as well as its structural properties. The diffraction peaks are accurately measured with XRD, which gives information about homogeneous and inhomogeneous strains. So by looking at the diffraction patterns, which we can measure from using X-ray diffraction or XRD, that will tell us about the homogeneity and inhomogeneity of this material, the specimen which we are taking it as this material which we are taking it as specimen, in this case to study the X-ray diffraction of that specimen. So if there is no inhomogeneous strain, the crystalline size D can be estimated from the peak width with Scherer's formula. Okay, so we can look at the, if there is no inhomogeneous strain, there is only homogeneous strain, then we will so there are whatever crystal is there, we can look at the crystalline structure, or suppose what kind of crystalline size. So there are different crystallines inside this crystal, so we can look at the size of this crystalline using this Scherer's formula. Only if there is no inhomogeneous. There is no inhomogeneous strain. If there is only homogeneous strain, in that case, homogeneity means there are all the crystallites that are present in the crystal are of the same crystalline structure. So then we can find out the crystalline size using Scherer's formula, using peak with Scherer's formula. So the Scherer's formula is given this. So D is crystalline size. So D, here D is crystallite size. Okay, so crystallite size, because if there is no inhomogeneous strain, there is only homogeneous strain. Because there is only homogeneous strain, we can look at the size of the crystallite and using this formula K lambda by B cos theta B. Okay, so this crystallite size D is equal to K into lambda divided by B into cos theta B. Okay, so here lambda is wavelength of the incident light and B is the full width of maximum of diffraction peak. So as we have discussed in the earlier slide, there are, if you plot the intensity distribution, you can see there are peaks. So from the peak we can look at the full width of maxima, right? Full width of maxima of using this intensity distribution peak. And then theta B is the diffraction angle. So theta B is the diffraction angle, lambda is the wavelength, and B is the full width of maximum of diffraction peaks, and K is Scherer's constant of the order of unity for ordinary crystals. So this K is nothing but Scherer's constant. In general, we take it as 1 because for ordinary crystals, the Scherer's constant is 1. Lambda is wavelength, B is full width of maximum of the diffraction peaks, and theta B is the diffraction angle. So using this Scherer's formula, we can calculate the crystallite size. Because there is no inhomogeneous strain, there is only homogeneous strain. That means in the crystal, whatever grains that are present are having of the same crystallite. Okay. So what is the use of this X-ray diffraction? So XRD is useful for the following applications: study of interplanar spacing. So D is nothing but interplanar spacing. We can study the interplanar spacing using X-ray diffraction. And we can study the mixtures, different mixtures, chemical and mixtures of alloys. We can study the mixtures. We can study the crystal symmetry, what kind of symmetry does the crystal possess, and we can look at the alloys. We can study the alloys stress determination in metals. We can also look at the particle size, for example, using Scherer's formula. Okay. So using the X-ray diffraction, we can study various say properties and symmetries, properties of mixture, interplanar spacing, mixtures, particle size, so on and so forth. So this is one of the characterization techniques, which is X-ray diffraction, to study crystal structure and structural properties of metals and alloys. The second characterization technique is transmission electron microscope, which is TEM. Okay, TEM, transmission electron microscope. So in TEM, electrons are accelerated from 10 kilo electron volts to 1 mega electron volts, projected onto a thin specimen with thickness less than 200 nanometers, right? So yeah, so the electron beam is projected onto the specimen by means of condenser lens system and penetrates the sample thickness either deflected or undeflected. So what is the use of this transmission electron microscope, or what happens in transmission electron microscope, which is one of the characterization techniques to study nanomaterials. Okay, so in this transmission electron microscope, electrons are accelerated. Electrons are accelerated from 10 kilo electron volts to 1 mega electron volts, projected onto a thin specimen with thickness less than 200 nanometers. So we are going to take a nanomaterial specimen whose thickness is less than 200 nanometers. So onto such a specimen, we are going to accelerate electrons from 10 kilo electron volts to 1 mega electron volts, right? So then the electron beam is projected onto the specimen by means of condenser lens system, and this beam is going to penetrate the sample thickness as deflected or undeflected. So this electron beam that is going to penetrate this sample, which is having thickness around 200 nanometers. So these beam can deflect or it can be undeflected. So the advantages of the TEM are its highest magnification. So the best advantage of this transmission electron microscope is that it has highest magnification. So it's very clear what we are looking at, up to the order of micron, and its ability to provide both image and diffraction information from a single sample. So using this transmission electron microscope, not only we are going to look at the image of the material, but also we are going to look at the diffraction information from the single sample. So this is one of the characterization techniques that is used to look at the highest magnification of a material up to order of micron size, and by using electron beam. So basically there are two scattering processes experienced by the electrons during the passes through specimen. So basically when we send or accelerate these electrons onto the specimen, there can be two kinds of scattering process that can occur. One is elastic scattering and the other one is inelastic scattering. So two types of scattering can occur, right? First one is elastic scattering and the second one is inelastic scattering. So elastic scattering involves no energy loss and gives rise to diffraction pattern. So if there is elastic scattering, then there is no energy loss and it gives rise to the diffraction pattern that we have discussed in the earlier slide. Suppose if there is inelastic scattering, inelastic interaction between primary electrons and secondary electrons at heterogeneities such as grain boundaries, dislocations, defects and density variations in the intensity of the transmitted electrons. So if the specimen has any heterogeneities, so heterogeneities such as dislocations, grain boundaries or defects, then there can be inelastic scattering between the primary electrons and the secondary electrons only at these heterogeneities. Okay, so we have two types of scatterings, elastic scattering and inelastic scattering. Elastic scattering can occur when there are no heterogeneities, but inelastic scattering can occur only when there are heterogeneities such as grain boundaries, dislocations, defects, and so on and so forth. So the eye magnification of resolution, the eye magnification or resolution of TEM, transmission electron microscope, is a result of small effective electron wavelength, okay, which is given by this equation. Okay, so why do we have this highest magnification or resolution using this transmission electron microscope is that the eye resolution or eye magnification is a result of small electron effective wavelength, so which is given by the wave equation lambda is equal to h by square root 2 m EV or QV, where V is the potential that is experienced by this charged particle electron, and this wavelength is given by the de Broglie. Right, so this is de Broglie's equation, wavelength equation, de Broglie's wavelength equation for a charged particle. So the highest magnification or eye resolution of this transmission electron microscope is coming from the effective electron wavelength given by this lambda is equal to h by square root 2 m EV, where m is mass of electron, E is electron charge, okay, and h is Planck's constant, and v is potential difference through which electrons are accelerated. So the higher the operating voltage of a TEM, greater is the lateral spatial resolution. So as we consider more and more higher voltage of this transmission electron microscope or the acceleration of these electrons, we are going to see higher lateral spatial resolution. So the disadvantage of this transmission electron microscope is its limited depth resolution. So we cannot see, we cannot look at for longer depth. We can use only limited depth resolution. So this is one of the disadvantage of this transmission electron microscope. So yeah, so we have the best advantage of this transmission electron microscope is its resolution and image. We can look at the material up to an order of micron, but the disadvantage is that we cannot go too deep into a material. Transmission electron microscope can be used to determine the melting point of nanocrystals. We can use TEM to find out the melting point of nanocrystals. An electron beam is used to heat up nanocrystals, and melting points are decided by the disappearance of diffracted pattern. So transmission electron microscopy is used to find out the melting point of nanocrystals, and also electron beam is used to heat up nanocrystals. We can heat the nanocrystal using this electron beam, and we can find out the melting point by looking at the diffraction pattern. Whenever this diffraction pattern disappears, then we find that temperature as the melting point of the nanocrystal. So transmission electron microscope can be used to measure the mechanical and electrical properties of individual nanowires and nanotubes. So we can use transmission electron microscope also not only to look at the melting points of these nanocrystals, but also we can use to measure the mechanical and electrical properties of individual nanowires and nanotubes. So for the nanowires and nanotubes, we can look at the mechanical and electrical properties using this transmission electron microscope. So these are some of the advantages of the transmission electron microscope, which we can use to look at different properties of these materials. So transmission electron microscope, this is the schematic of this experimental setup of transmission electron microscope, where you have this electron gun on through which you are going to shoot the electrons onto a specimen, right? So this is the specimen and this is the condenser lens, and these electrons are going to penetrate to the sample, and then they are going to get deflected or undeflected, through which we are going to get the information, image, as well as the this resolution around up to micron size. Okay, so we can see the image on this fluorescent screen here. So this is the schematic representation of the experimental setup of transmission electron microscope. So this transmission electron microscope gives the following information. For example, morphology. We can look at the morphology of this material, the size, shape and arrangement of particles, as well as their relationship to one another. So using transmission electron microscope, we can look at the morphology, and in the morphology we can look at the size, shape, arrangement of particles, as well as their relationships to one another on the scale of atomic diameter. So around angstrom scale, we can look at the morphology of these materials. Crystallographic information. Using this transmission electron microscope, we can also look at the crystallographic information, the arrangement of atoms in the specimen and their degrees of order, detection of atomic scale defects for a few nanometers in diameter. So we can look at the arrangement of atoms in the specimen. So how do they order, and so we can look at the order of the atoms in any nanomaterial up to that atomic scale. We can also look at the atomic scale defects for a few nanometers in diameter. Compositional information. So we using this transmission electron microscope, we can also look at the compositional information. For example, the elements and compounds of the sample is composed of their respective relative ratios. So what kind of ratios? Suppose we are taking any element, any material. So in the material there can be different components, and what is the composition of each component? So that can also we can find out using this transmission electron microscope. So yeah, so these are some of the textbooks which I have used in this presentation, and this is some of the reference books which we can use to look up for the further information. So to summarize, in this presentation I have discussed about the characterization techniques. So characterization techniques to study the nanomaterials. Characterization techniques. So I have discussed about two important characterization techniques. The first one is X-ray diffraction. X-ray diffraction. So which is also called as XRD in short. XRD. So the second one I have discussed about is transmission electron microscope. Transmission electron microscope. So which is in short called as TEM. So these are the two experimental techniques I have discussed to study the properties of nanomaterials. So XRD is to look at the crystal structure, and structural properties of metals and alloys. And transmission electron microscopy is going to tell us about the image or morphology of materials, because this it is high, it gives us high resolution up to order of resolution or magnification. Okay, so resolution is resolution of order micron. So up to micron scale we can look at the high resolution into a material. So we can look at the morphology and compositional information using this transmission electron microscope. So these are some of the two characterization techniques to study the crystal structure and structural properties as well as morphology of nanomaterials. And yeah, so I am going to end this presentation here, and in the next presentation I am going to discuss about some numerical problems on nanotechnology. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.